to talk about one of the problems from the quiz real quick, and then if there are others you guys want to look at, we can do that too. But one that I, noticed, and I mean, I anticipated it being one that, we would maybe have kind of the most struggle with. But 1b, so the log of the square root of x squared y over 100. So first of all, this is a common log, so log base 10, right? We usually suppress the base when it's 10 for, I don't know, reasons, I guess, but it does mean base 10. So things to notice here first would be the division, right? It's a quotient. That means we can split this up into two separate logs by subtracting to get smaller, simpler pieces, right? Now this is a purely numeric thing, right? It's the log base 10 of 100, which you can do with a calculator or by looking at it if you're comfortable with that idea. What power of 10 is 100? Well, it's 10 squared, so that's just 2. Anytime you've got numeric terms in something like this, just be sure to check to see if they clean up nicely. If it doesn't come out to a whole number, don't worry about it. But if it does, we'll be looking for you to clean that kind of stuff up. And then here, there are a few ways you could, like orders you could do this. It is a product. There's also a square root. I would probably simplify this to first deal with kind of breaking up that square root of x squared. This is the same thing as the log of x times the square root of y, right? The square root of a product is just the product of the individual roots. So you've got the square root of x squared, which is x, and then the square root of y, which is the square root of y. And then because there's a product there, we can break that up as well. So we get the log of x plus the log of the square root of y, using the product rule there. I can't do anything else to simplify this. Can't do anything else to simplify that. But the log of the square root of y, a square root is the same thing as raising that to the 1/2 power. So you can use the power rule to bring that out. Log of x, 1/2 times the log of y minus 2. That would be this thing fully simplified. Kind of the goal is getting each of the log terms that were made to the lowest, simplest possible terms, which means they can't have multiplication or division or exponents inside them, right? If there's addition or subtraction somewhere, like if this was x plus 1 inside the log, I can't do anything to break that up, but I can't leave any multiplication, division, or exponents inside a log. Okay? And then, of course, once you're a little more comfortable with it or whatever, of course, some of these things you could do at once, right? I kind of wrote out every single thing. It doesn't have to happen in 5 separate steps. Are there any others that you guys want to talk about or look at from the quiz that I just handed back? And if you emailed that to me, you should have gotten an email back from me, acknowledging and grading and stuff. So if you didn't, let me know. Everything else is okay? Seemed like everything else, for the most part, went okay. 1 or 2 places where, maybe you didn't show enough detail on something like the inequality maybe. But most of the rest of it went pretty well. Okie dokie. Homework stuff going okay? Anything we need to talk about there? Okay. Yesterday we left off right here. I think we may have set these up or set one of them up, but we'll just kind of run through that again anyway. So we've got these 2 compound interest formulas for periodic or continuous compounding that look like that. Again, those formulas will be given on a test, right? You don't need to try to memorize them or anything. Make sure you know when to use which one and what all the stuff is. So did we actually set these up? I mean, I know I said like go home and finish them, but did we set them up?
Yeah,
we set them up. Okay. So the first one, we're compounding quarterly, which means that n is 4. Okay, that is a little aggressive, which means that n is 4, and also that we're using the periodic compounding formula. We are starting with $2,500 principal, 1.7%, so 0.017. To the 4, we don't know t, right? The question is how long, so we don't know t. We're going to need to solve for that. And we want to save up to 3,000. So we're looking for how long it's going to take for my $2,500 to turn into $3,000 at such and such interest rate. On the other hand, the other situation, we're compounding continuously, so we use the other formula. But other than that, the setup's pretty similar. We want A to be 3,000, P to be 2,500, and we still don't know T. And since I don't have any room to work right there, we'll pick these up and move them someplace else. Okay. Now we need to solve for T. What do you want to do? Divide by 2,500. 3,000 divided by 2,500. 1.2? Okay. 1.2, and importantly, that's not rounded, right? It's exactly 1.2. That's reduces to 6/5, so it's exactly 1.2. Don't round in the middle, because if you round in the middle, you'll probably be off by enough at the end for at least the computer to count it wrong, right? And me to write some kind of grumpy note about like, hey, don't round in the middle. Remember all the times I said that? It'll cost you a point or something on a test question, but it'll be enough for the computer to count it wrong, and that's annoying. So this is the exact value. If it's some messy decimal thing, leave it as a fraction or store it in your calculator or whatever, right? Okay, and speaking of which, let's clean this up a little bit. One plus 0.017 over 4. I'm going to keep that whole thing because, again, I don't want to round in the middle. I know, writing down a number with 5 decimal digits makes us all a little bit uncomfortable, but we're just going to keep that whole thing. Again, the Desmos isn't rounding here or anything. That's the exact value. So 1.00425. And we're still trying to solve for t. So now what? Keep in mind that the thing on the left is not just that number. It's that number raised to a power and a power that we don't yet know, right? So we can't divide by it. If you divide both sides by this, all you're going to do is change this to 14 minus 1. Right? Like all you're going to do is take 1 away from this. It's not going to make it go away. We have a power we don't know. Forget about the fact that the numbers are a little bit messier than we're used to. A power that you don't know, what do you do? A log. Yeah. You got a base and an exponent and a, answer, right? Rewrite it as a log, and what does that turn into? The log with base that, which again feels a little bit weird, but your calculator is going to do it for you anyway, right? Of 1.2 is equal to 4t. Then just divide by 4. So t is Well, again, this log with a weird base of a decimal number, which all makes me a little bit uncomfortable, but again, we're not doing any of it by hand anyway, so it doesn't really matter, right? Your calculator is perfectly happy treating the base as 1.00425 as it is with using base 2 or base 5 or whatever, right? And you know how to do that at this point. If you don't, come talk to me. What's T? How much? I'm sorry. 10.74. Okay, let's go with 10.7. Sorry, the white noise from the thing is like at exactly the same frequency as. So about 10.7 years. And again, like I know the numbers are a little messier here, right? And that always just kind of throws us off track a little bit. But look at what we really did. Exponential thing with the power I don't know. You know, cover up the part that makes you uncomfortable if you want. Number raised to an exponent I don't know. What we need to do is get it by itself and then take a log, right? Okay, so how does the other one work? Exactly the same way. Thank you. Yes, divide by 2,500. 1.2. This is actually, it's kind of ironic because this is actually messier. E is a transcendental number. E's got infinitely many decimal places, right? But it looks cleaner because we write it as an E, right? Now, exponential that we don't know, right? The base is E, so rewrite it using natural log. So T is the natural log of 1.2 divided by 0.014. So let me give you that when you have it. How much? 13? 13 point what? 0.02. Okay, so yeah, 13, 0.0, I guess. Or just 13 is fine. I wasn't specific about how to round here. I would be specific about, round to like the nearest tenth on something like a test question. Now, again, we don't always have a great number sense about, whether answers make sense or not. But the fact that these are close to the same, right? We're talking about the same amount of money. The interest rates are comparable, right? There's a difference in the sort of scheduling for how they're compounded, but it makes sense that these would be kind of in the same ballpark, right? If I got 10.7 for one of them and the other one came out to be 300 or 0.1 or something, I would probably want to rethink, one or both and make sure that I set things up right, make sure I didn't make a mistake keying things in somewhere, because it makes sense that these are, kind of on the same, scale. Okay? Yeah, go ahead.
Are the formulas going to be on the test?
Yes. So the test will have, so like here's the cover page that you've been getting on the last couple. I'm just going to add those to it. So the cover page for this test and then the final will be similar. We'll have those on it as well. Okay, so you still have the quadratic formula and the vertex thing in case you need them, but it'll have those interest formulas as well. That's not what I wanted to do. Okay. Anything else about the sort of money stuff? You feel pretty good about that?
Wait, if it says which account should we choose,
Well, I don't know. What do you think? Which one should we choose? The one that gets you there faster. Yeah, so we figured out that this one took about 10.7 years. This one took about 13 years. So which should you choose? That one. But think about the full context of the situation. You've got some cash on hand. You're trying to, invest to save up a down payment for a new car. If it takes you a little over a decade, like that's probably not really that viable a plan, right? It's probably not going to be there anymore. The down payment amounts could be different, right? Yeah, so yes, that's the one that gets there faster, but probably I need to rethink the plan anyway. Okay. Okay. All right. So I think I mean, obviously, like for class purposes, know how to work the problems and stuff. There are a good amount in the homework. There's some on the reviews and stuff. I feel like I've kind of been emphasizing the money stuff is important. You might read into that a little bit as far as what to expect next week. But the takeaway for like life purposes is figure out how to make compound interest work for you, not for the people you borrow money from, right? Actually, like after we talked about my recent experiences in financing, they called me yesterday afternoon to like make sure that everything go okay. You got all the terms and stuff. I was like, yeah, and I used you as an example in class today of why it's important that I asked like 3 times. I was like, okay, so this is the date by which I need to have. Yes, okay, all right, good to go. And then I set several alarms in my phone to make sure that for a week ahead of time. Okay, so let's take a look at another example of a continuous sort of growth thing. So this continuous interest formula, right? A equals P times E to the RT. These are the labels we give it when we're talking about money, right? The value or the amount of the account, the loan, whatever, the principal, the interest rate, the time. But E, again, is the thing that controls this sort of continuous growth. There are lots of other examples where you see something that has this same basic shape, right? Something times E to some power that deal with continuous growth. So if you talk about modeling population growth, it looks a lot like this. There's an example of that in either the test review or the practice. And somewhere there's one about like, I think it's about like bacterial growth in culture or something, but like it looks almost identical to this, right? You just use different labels, but they mean kind of the same thing. This next example, radioactive decay, let's start with just looking at this thing. Apart from the fact that the letters are different, A of t, this is just function notation, right? So I'm calling the function A and the variable t for time again. This is a subscript. So if you haven't seen this before, these come up all over the place in natural sciences and like chemistry, physics, biology, that kind of stuff, to mean what happens initially, right? When the time was 0, when we started, measuring from it or whatever, this was the amount that we started with. So this is just a subscript. A means the amount of something that we'll talk about in a minute. The 0 subscript just means the beginning amount. E, okay, there's E again. To the K times T, hey, time again. So this K is just a rate constant that means something like the interest rate from what we just looked at, right? Now in this context, we don't think about it as a percentage, but this, if you kind of put it side by side with this, looks a lot like it, right? They look very similar, and there's a reason. It's the same model. It's the same relationship. They work the same way. The way you solve is exactly the same. Just the interpretation is a little bit different. We'll come back to this or jump to the other one real quick and take a look at it. This, at face value, looks a little bit scarier, but look at what's actually happening. Focus on this part. Hey, there's another E to some power, and that power's got a T in it and some other constant, right? This part's pretty much the same. This, well, it's a difference of two things, but this is just some number again, sitting out in front, right? So P, E to the RT. Again, this has a very similar feel to it, except here I'm subtracting two things. We'll talk about why in a minute. And then we're adding something on at the end here. What does adding something there do? Just moves the whole thing up, right? That's all it does. It's just a vertical shift. So again, this is pretty much the same model, pretty much the same idea, just with different labels and a different interpretation. And you'll see a couple of others as you go through homework and reviews and stuff, where it's, essentially the same problem, just in a different context. Okay. So radioactive decay. The thing that makes radioactive stuff radioactive is that it's unstable. So if you've talked about this in chemistry or whatever, you may know a little bit about this, but it's unstable. Something about the nuclear structure of it or whatever, it breaks down over time. And as it breaks down, it shoots off, I don't know, neutrons and protons and whatever else atoms have in them. They shoot off, and that's what makes it, dangerous. That's what makes it glow in the dark, or warm your food up in the microwave, or give you cancer if you hang out next to it for too long. All that kind of stuff, right? So it decays over time, and that decay can be used for some things, right? One thing that they use it for is radioactive dating. So some archaeologist type finds a, I don't know, clay pot buried in the ground in Greece or something. They can measure the amount of certain things that are in it and know, well, okay, here's how much ought to be there. Here's how much is actually there. So this must be 20,000 years old or whatever, right? This is a very rough idea of how the thing works, but the modeling works exactly the same way as the continuous interest thing. The only difference is that instead of growing over time, like the money in a bank account would, the amount of this radioactive material decays over time. What that means is that this is going to be negative. To force the thing to decay. Apart from that, everything works the same way. It's just the interpretation and the context is a little bit different. Okay. So if we are given a statement like this, the half-life of carbon-14, the 14 part is just how you name the isotope. It's the number of neutrons it has or something. I don't know. It doesn't matter. We're not chemists, right? It's the atomic weight. So the 14 isn't the number that we care about. It's just part of the name. The half-life of this particular radioactive isotope is 5,730 years. What we want to do is find the exponential decay model for that particular isotope. What that means is we need to find K. In the interest problems that we talked about yesterday, R, the thing that lived where K lives now, was an interest rate, right? That's a thing that's fixed and set by the bank or the lender or whatever, right? They say, hey, you get 2.5% interest. I say, okay, cool. And then I live with that and work with it. And that's the only thing that tells me about how I model stuff in that account, right? For a particular radioactive isotope like this, K plays the role of R, but it's fixed, right? It depends on that material. That material decays at a certain rate. When we talk about the half-life, well, what does the name half-life sound like it tells you about? Yeah, how long it takes before a pile that used to be this big is half the size of what you started with. That's all. Right? It doesn't really go away. It just changes into something else as it breaks down. But if you start with 1 pound of carbon-14 and you come back and check on it 5,730 years later, now there's half a pound, right? Okay. That's a weird way to use your time machine if you have one, by the way. I've got some other thoughts on how we could use the ability to time travel rather than checking on a pile of carbon-14, but that's for another time, I guess. So if we want to find the exponential decay model, and what that really means is finding K, and all that we know is the half-life. And the model looks like A equals A naught, E to, or A sub 0, K, T. What do we for sure have information about? Yeah. We definitely don't know K because the whole thing was find K, right? That's the part I gave you a hint about. We know that T is 5,730. We don't know K, but we know that we don't know K, right? We know that we're looking for K. But I didn't give you any amounts, right? If I said like, hey, you got 100 grams of it, you know, how long is it going to take before it's 50 grams or whatever, then I would just plug those amounts in. I didn't give you anything, but I also didn't need to, because what do we know about this amount of time for this material? There's going to be half of it left. So this is kind of like the how long does it take for it to double thing we looked at yesterday, right? So I need something here, right? I need to fill in something for A and for A naught in order to work the problem. But the important thing isn't the values that we give it, it's the relationship. Okay? So somebody, how much carbon-14 do you have in your pocket right now? Hopefully none. But...
I got 3.
Okay. Yeah, let's pick an even number.
Oh, okay.
Let's say 4. 4 carbon-14s in my pocket right now. After this much time goes by, how much should be left? 2. Half.
Yeah, why did you change that?
This is how much you started with. After time goes by, so for the interest stuff we talked about yesterday, you put money in a bank account, that amount of money grows, right? They pay you interest. Or you borrow money, that the amount you owe grows, right? This is decaying, it's breaking down. There's less of it over time. So as time passes, this number, the outcome, the amount you end up with, should be smaller than the amount you started with, right? So it's the same situation, only kind of reversed, right? Because it's decaying rather than growing. So choose a value for this, how much you started with, right? Pick your favorite number, whatever. This ought to be half as much, okay? Now, like we saw yesterday with the interest thing and the doubling, the actual amount that I picked doesn't really matter, because what are we going to do right off the bat? Do it? Not yet. As soon as we get the E term by itself again. First thing we're going to do is divide by 4. And 2 divided by 4 is 1/2. And that's why I didn't care so much about what actual numbers I picked here and here, but I cared about the fact that this needs to be half of that, right? Notice that this says the same thing. This is like starting with 1 carbon-14 and ending up with a half of 1, right? Or 1 pound and a half a pound or whatever. So whichever version makes more sense to you, you know, pick something here and then take half of that amount here, or just say, okay, I want to know when the exponential term is the same thing as multiplying by half. Right? Which, if you look back at that problem about doubling yesterday, it was the same idea. Only there we looked for where the exponential was the same thing as multiplying by 2. Right? So we have the exponential thing equal to 2. Here it's equal to a half, because again, we're talking about half-life for something that's breaking down over time. Now we can rewrite it as a natural log. Right? Base E all by itself, rewrite it as a log. What does that look like? Yep. Which means that K is how much? That sounds high. Okay. Yeah, let's talk about this. Okay, log of 1/2 divided by 5730, is that right? Yeah. Okay, so if your calculator gave you, somebody read me what you had.
-1.2096809.
Okay. And then at the end, E, -4. Okay, this is scientific notation. So because this is a really small number with leading zeros after the decimal, this means the same thing as times 10 to the negative 4, right? Which means slide the decimal over 1, 2, 3, 4 places and then fill in zeros. So it's the same thing as negative point, 1, 2, 3 zeros, 1, 2, and then let's round it to 1, 2, 1. Do it. So whatever this value is, like if your calculator gives you a, E with some number following, that means how many places you're going to slide it over. Did your calculator just give you the number? Okay, yeah, you're good. Yeah, you just have the number. If yours doesn't, say like e to the minus 4 or whatever, then you're good to go. That's just the number, right? But if it does give it to you in scientific notation, that's how you translate, right? This is the actual value. That's kind of the way this tends to go for unless the half-life is like really, really short, that K value ends up being something really small. So 0.000121. Then we have our model. So we found K. That's what K is for this same material all the time. So beyond that, answering these other questions, we want to estimate to the nearest tenth of a year. Now what are we finding? T. How long it would take for a 500 gram sample to decay to 400 grams. We've got amounts for A and for A naught. We know what K is now, and we're trying to find T. So how would that, what would setting that up look like? 400 equals 500 e to the negative 0.000121 t. The question was how long, so I know that I don't know t yet, right? I'm expecting to need to find t. You solve that for t. Hey, what's solving that going to look like? Exactly like what we just did, right? Divide by 500, take a log, divide the thing over, get t. Hopefully you're picking up on the fact that the actual solving process for all of these is pretty much the exact same thing, right? You kind of follow the same steps. The thing we don't know is in an exponent, so we need to get the exponential thing by itself. Here that means dividing, then take a log, then finish what's left. Okay, so I'll leave that one for y'all to finish. What would the setup look like on part C? What are we given? Estimate how much of a sample will remain after 500 years. So we've definitely got T. We know K already. Which amount do we have and which one are we looking for? Yeah, we have the starting amount. And that means we're looking for A. Oh, hey, we don't actually have to solve anything here. This is just a set it up and punch it all into a calculator, right? Just evaluate the function. In other words, this is like saying, hey, if I started with 300 and want to see what happens after 500 years, right? That's what this question is asking. Now, again, a couple places that you can sort of think about things to check yourself a little bit. This is how long things should take. So T's got to be positive, right? If you get things switched somewhere in setting it up and get a negative T value, time's not negative, right? So something went wrong. Here, again, I know that this should be some positive number because we're never going to, have a negative amount of something. So it's got to be something positive. Okay, so y'all finish those. Solutions are in Blackboard. You can check those. We can talk about it next time if you want. Let's talk about one more example real quick. Newton's law of cooling. So if I take a warmer object into a colder room, right? Like if I ordered a pizza and set it in the middle of this, it's not bad now, but I am wearing a much heavier jacket than usual. In this cooler room, how long is it going to take to, or how is it going to cool down to, room temperature, right? It's going to match the temperature of the room eventually. So heat transfer, and there's a corresponding thing for if you put a bucket of ice in the middle of the room, how it warms up, right? It's the same idea, just different directions. This e to the minus RT thing, this being negative means this is decaying, so it's a warm thing cooling down. If you flip that sign, you could talk about a cool thing warming up, right? But it works the same way. That's going to depend on a couple of things. One would be the temperature of the object itself, right? The way that this banana that was maybe 5 or 10 degrees warmer than the room, the way it cooled down when I brought it in is different than if I set a pot of boiling water in the room, right? Because that's much hotter. That's going to cool down on a different time scale, a different time frame. So that matters. That's this. Right, again, 0 subscript means what happened at the beginning. That's the initial temperature. Of whatever object we're talking about. The other thing that's probably going to be important is that if I take something and set it in a room that's at a different temperature, it's only going to cool down to match the temperature of the room, right? Like I'm not going to bring a set of pizza in here and come back a couple hours later and find that it's, well, okay, I was going to say find that it's frozen. Like maybe we would in this case, but I'm not going to find that it's like negative 200 degrees or something, right? So the other thing that matters is the temperature of the room. That's this, A for ambient. If you look at where that shows up, a lot of this stuff should kind of fall into place a little bit. T naught, the initial temperature of the object, minus TA, the ambient temperature, that's just how different are they, right? That's the thing that's really going to matter. It's not so much the fact that, the pot of boiling water is 200 degrees or whatever. 212, I know what the boiling point is. It's not so much that on its own matters, because if I put that in a room that's, like a sauna, like 150 degrees or something, that's going to work differently than if I set it in this room that's, somewhere in the 40s, right? That's why we take the difference in these two things. And then plus T sub egg, and what's that do to the function? Adding something that's a vertical shift, right? Exponentials have a horizontal asymptote. If you apply a vertical shift, what's that do to that vertical or that horizontal asymptote? Moves it up, right? So this exponential thing that's decaying, what it's going to decay toward is that horizontal asymptote, which is at whatever T sub A is. That means the thing is going to cool down to the room temperature, right? Like that's what's happening here. E is still E, T is still time. We're going to measure time in minutes. And then R, again, is like a rate constant thing that depends on the material, right? A pot of water is going to cool differently than a pizza or a block of steel or whatever, right? Like the material matters.
For that one, it can change from negative to positive.
So the only thing that would change this from negative to positive would be the difference between talking about a warm thing cooling down versus a cool thing warming up, right? Because our function looks like this. We're treating the y-axis basically as the temperature, and the x-axis is time. So warm thing cooling down, the temperature's dropping. Cool thing warming up would look like that, and the only difference would be that you wouldn't have that negative sign there. Okay? if you needed it. Right. Yeah. The point here really is to see that, again, this turns out to really just be the same model, right? The only difference is that it's got this vertical shift because it's only going to drop down to the room temperature, not to zero, right? The exponential or the radioactive decay thing, after a long enough time, that lump of radioactive stuff isn't going to be radioactive anymore. There's going to be zero remaining, right? So it decays to zero. This decays just to the room temp. Okay, so a pot of boiling water with an initial temperature of 212 degrees is in a 78-degree room. If the R value, so I'm giving you R here, what is the temperature of the water after 15 minutes? What do we know? What are we trying to find? We're finding T. T, and really it's T of 15, right? Like the one that's on the left-hand side. We have the initial temperature. What is it? 212. What else do we have? Minus 78. We have the ambient temperature, the room temperature. E, negative. Okay, real quick here, just because there could be some confusion about this. Depending on where you look and how things are stated, sometimes, it'll have the negative sort of built in there. Sometimes it won't. I just realized that when I wrote this, I didn't think about that. What I mean here is that this whole like R term in the exponent should be negative, right? So I don't mean like take the negative and then they cancel. What I mean is that this should look like 0.0284, 4 times T, which is 15. Okay? So for a thing that's cooling down, that exponent needs to be negative. For a thing that's warming up, the exponent needs to be positive. Okay? The same thing's true for the decay thing. Sometimes you'll see that decay model written like this. What it's really saying is just that this thing overall has to be negative in order for it to be decaying, right? So depending on where you look, sometimes it'll be written one way or the other. Plus 78. Okay, so the temperature of the object minus the room temperature, because we want to know how different they are, right? How far apart they are. If they're close together, the change is, going to be kind of more gradual. If they're far apart, it's going to be more dramatic at first, as they, kind of come toward the same temp. This is just a number. This is just a number. If you actually look at this, there's not really anything for us to work out, right? We don't need to solve anything. We just need to know what this number is. So punch it all into a calculator. About what should we expect for an answer?
2 hours and 45 minutes.
We're looking for a temperature, right? We had okay, 165. Yeah, we're looking for a temperature. It's got to be between what and what? 78 and 212, right? It was 212 to begin with. It's going to start cooling down. The room's at 78 degrees. It can't drop any lower than that because that's not how things work. So 165 makes sense as an answer, right? And that would be degrees because this is temperature. We were given the time, 15 minutes. We're looking for the temperature. No, who cares? No, I don't right now. Let's just go with 165. Okay. How about 6? Deliver a pizza to a room. The pizza's at 150 degrees. The room's 75. If the pizza is cooled to 100 degrees after 10 minutes, how long will it take for it to cool to 90? I gave you a hint that what we need to find is R to begin with. Ignore that part for the moment. we've got an initial temp. We've got an ambient or room temperature. We've got a temperature after some time has passed. And we've got a time. Yeah, sorry. It's like function notation, right? It's like T of 10, right? The temperature at 10 minutes. So it's not 100 times 10. It's that when little t is 10, big T is 100. Okay? So 100 equals 150 minus 75 e to the, we don't know r yet, times 10 plus 75. But we have enough information there to solve for r. Then the second part of the question says, how long will it take for it to cool to 90 degrees? How long? We want to find t, right? It's not 10 anymore. It's got to be a little bit longer than 10. The setup's going to look pretty similar, only the difference is now we know what r is. From over here, but we don't know what t is. Now, the actual mechanics of what you do to solve are identical, right? You're finding a different thing, but you do all the same stuff. Combine these, subtract, divide, take a log, finish solving to get r. Once you have r, combine these, subtract, divide, take a log, finish solving, but you'll be finding t instead. Right, so the actual like steps are the same, but you kind of have to do it in like a two-step sort of thing, right? It's similar to what we did the page before with the radioactive decay thing, only there I broke it out into two separate like questions, right? But we did the same thing. First we had to find k, then we had to use k to find something else. Here we have to find r, then we have to use r to find something else. Okay? All right, now if you haven't already, get into the homework for this week and work on some problems. Some of these things show up directly, some of them do not show up directly.